Hi everyone, welcome to the first video of Module 10 for Kinese 7103, which is taught in the Department of Health Kinesiology and Recreation here at the University of Utah. In today's module, we're going to be talking about models with non-independent error terms. So this can refer to situations in which we're taking repeated measures from within a person, or we might have people who are statistically nested in some way. So for instance, we might have students within classrooms or classrooms within schools, and these groupings in the data are going to lead us to non-independent error terms, and we need to know how to deal with those. So far, we've been dealing with situations in which we have independent and identically distributed data. So that means we have important assumptions that we're making about our residuals when we're calculating p-values, whether those are p-values for t-tests, f-tests, omnibus f-tests, whatever it is. If we're making those statistical inferences, they depend on certain assumptions. And sometimes our analysis is relatively robust to these assumptions, which is to say, even if this assumption is violated, it doesn't change the answer too much. And other times, the assumptions the models are not robust to violations of the assumptions, which means if you violate this assumption, it changes your answer a lot. So normality is one which we generally, assume when we're doing these general linear models. We assume normality of the residuals. Now, we're relatively robust to violations of normality, but we have other assumptions that we care about. So for instance, we also assume that we have a constant variance. This is what's referred to as homoscedasticity, or the homogeneity of variance, if you remember from many chapters ago in the book. And we're going to be talking a lot about these in the subsequent chapter when we talk about testing these assumptions, what happens if they're violated, and how bad the situation is if they are violated. But the major one we want to focus on today is the assumption of independence, right? We assume that each of our residuals are statistically independent of each other, which is to say that they are not correlated, right? Knowing something about one person's residual doesn't tell me something about another residual in my data set. And this is something we are not robust to violations of. If we violate our independence assumption, we're going to be getting the wrong answer, and we're going to probably be missing crucial information that's in our data because we're conflating different sources of variance. So we have to really understand what it means for our data to be statistically independent and correctly identify the way in which our variables are crossed or nested within the data. So we have different types of non-independence. Okay, so we can have positive sources of non-independence in which linked data are more alike than non-linked data. So for instance, in this case, if we're looking at proficiency on mathematical aptitude tests at 4 different schools, right? Maybe for schools that have a stronger math department, their Calculus 1 scores and their college algebra scores will both tend to be higher. So we see in this situation a difference between Calculus 1 and college algebra, right? The level of mathematical proficiency for students in those two classes is different. But we also see a positive non-independence because schools where they score higher on Calculus 1 are also schools in which they score higher on college algebra. Similarly, we can have a negative non-independence, which is where linked data are more likely to be different than non-linked data. So in sort of a similar example, if we look at proficiency versus growth on mathematical aptitude tests in 4 different schools, we might have schools that have different levels of end-of-term performance. So we have some very high-performing schools and some relatively low-performing schools. But we can then look at how much do they change over time. And maybe schools who are performing worse, right, actually changed quite a bit over the course of the semester, whereas those schools where students, at the end, it looks like, hey, they know more math, they didn't actually learn more math, though, over the course of the semester. It's true that they're at a higher level of aptitude overall, right? But did they actually improve to a greater degree in order to reach that high level, right? So this is a situation in which we're going to find that schools that showed lower values here might show higher values here. So negative values are going with positive values, and the data are more different within a school than they are across schools. So that would be a case of negative non-independence in which we have a negative correlation between our data sets. So in practice, non-independence is going to arise from a variety of factors. This might be, if we're measuring time within a person, kids within schools, patients seeing different therapists, hospitals within counties, right? There's lots of ways that our data might be clustered that is going to create a statistical dependence that makes some observations more alike or some observations more different. Broadly speaking, I like to think about this as two different sources of dependence you get from either being grouped or being sequential in some way. So to use sort of a sports analogy, a good one is that players are grouped within teams, right? So that creates one sort of dependence, right? If I have players on, let's say, the Green Bay Packers, the Cleveland Browns, right, and the New England Patriots, right? Individual players on the Patriots are more likely to have success just by virtue of the fact that they're on the Patriots relative to the Browns, right? So I can't really say that player H is necessarily a better player than player E because there are between team differences that might be affecting my data. Similarly, if we have sequential effects, that can create either positive or negative non-independence. And usually it's going to create positive non-independence because if I'm measuring players over time, a player's performance in year one is going to be more similar to their performance in year 2 than it is to years 3 or 4. And we get what's known as an autoregressive correlation structure where things that are close together in time tend to be more similar than things that are farther apart in time. But whether we have groups or sequences, right, these all create non-independence in our data, and we need to learn how to implement statistical models that adequately deal with this non-independence so that we can actually analyze the data to measure the effects that we're interested in. So returning to our examples, there's a few different ways that this could work, right? And I want to really just illustrate this notion of the independence assumption being violated. So let's say that we had a hypothesis that scores were going to be different in Calculus 1 than they were in college algebra. I look at this, I have 8 different classes that I can compare. But in reality, I have classes that are nested within 4 schools, right? So school 1 has this class and this class, school 2 has this class and this class, and so on. So I don't actually have 8 independent observations. And if I were to implement this regression model, the mistake would become apparent because when we look at the residuals, right? So here, this is the difference between the calculus proficiency scores for this, the mathematical proficiency scores for this calculus class and the overall proficiency scores for all calculus classes, right? Creates a negative residual here. And then here's the proficiency scores for this college algebra class, and the overall proficiency score for all college algebra classes creates a negative residual here. And you can see that in our residuals, negative values go together and positive values go together. So we have positive non-independence between schools because there's a positive correlation between these sets of residuals. And this is a major problem because if we violate the fact that classes are nested within schools, we violate one of the most critical assumptions of our inferential analysis. And if we do that, we can't really trust the p-values that we're generating, right? They aren't going to be accurate reflections that lead to reliable inferences. Similarly, if we have negative non-independence, right, where linked data are more different than non-linked data, we could be looking at this situation where I'm interested in maybe the difference between proficiency and growth over the term, right? And I might say, oh, well, I have 8 different observations here, but in reality, I have a proficiency score and a growth score, right, for one school. And then I have a proficiency score and a growth score for another school. So I don't actually have 8 independent observations. I have 4 sets of statistically dependent observations, right? And we can see that again, and if we take the residuals from this regression equation, if we treated these data inappropriately, what we would end up with is a difference between each data point and what our model estimates, right? So it's this data point and the mean proficiency score for end of term proficiency, and this data point and the mean change score for growth over the course of the term. And we'd find that we have a negative proficiency residual here and a positive growth residual here. For school number 2, we have a positive proficiency residual here, but a negative growth residual here. So again, clearly these residuals are not independent because we always have negatives and positives going together, which means that we have a negative correlation between the data points in our data. So if we ignore this data structure, right, and we ignore the fact that we're actually taking observations from within the same school, that violates a major assumption. And again, it's going to lead us to the wrong statistical inference. So the most important thing that we really want to, emphasize at this stage is we want to be very cautious of when we're looking at our data, what are the groupings or what are the sequences, right? How are our scores potentially statistically related to each other? And are we correctly accounting for that in our statistical models? So in the next few lectures, we're going to be walking through how to correctly do this in crossed and nested designs, or in more complicated designs in which we have crossed and nested variables. If you're not familiar with the terms crossed and nested, that's okay. We're going to be going into it in more detail. And you maybe have heard of sort of similar terms when people refer to within subjects factors and between subjects factors. So what we need to do, right, in order to handle the violation of this assumption is control the data so that we're no longer dealing with non-independent observations. And we can do this by partitioning the variance so that we remove the parts that are statistically dependent and focus only on those parts that are statistically independent. And the exact way in which we will do this depends on whether or not our data are crossed or nested. So what do we mean by that? Well, two factors are crossed when every level of one factor co-occurs in the design with every level of another factor. So for instance, if I have three conditions and every participant is in each of the three conditions, that is a crossed factor. Now, the sort of converse of that is a nested factor. So a factor is nested within another factor when each category of the first factor co-occurs with only one category of the other. So for instance, in a randomized controlled trial, participants are nested within groups because some participants are in the experimental group and some participants are in the control group. No participant is in both groups, which means that's not a cross factor. We have a nested factor. So in many experimental paradigms, you might refer to cross factors as within subject factors and nested factors as between subjects factors if your unit of analysis is a person, right? Because then if I have people who are in different groups, people are being nested within groups. And anything that then happens within a person, right? So if I have different conditions or different time points, that might be crossed at the subject level, which means it is a within subject variable, right? But it's important to understand that crossed and nested are a little more useful in a little more general terms, because as you're dealing with different sorts of experimental designs, the subject level might not be the level of analysis anymore. You might be looking at classroom attainment, or you might be looking at different summer camps where kids go to school, right? You might be looking at the performance of different hospitals. Or you might even be looking within a person to say, well, a limb maybe is the level of analysis, and I'm interested in how the dominant limb fares separate from the non-dominant limb, right? And we can have lots of different types of designs where it's more useful to think about these things as crossed and nested than as within and between subject. To illustrate, however, let's consider two different training programs for changing body composition. In this case, we're focusing on body fat percentage. So if we randomly assign participants to a high-intensity interval training program or an aerobic fitness program, and we measure them at a pre-test and a post-test. So I have 10 participants in HIIT training, 10 participants in aerobic training. They all come back, let's say 6 weeks later, for their post-test assessment. So now time and group are crossed factors because every group is represented at every level of time. So time and group are crossed. And you can see this if we do what we call a cross tabulation, right, by counting the number of observations as a function of time and as a function of group. We can also see that time and subject are cross factors because every subject, right, or every level of the subject variable is represented at every level of time. Each person has a pre-test assessment and a post-test assessment, so this would also be crossing of these two factors. However, participants are nested within groups because if we do these cross tabulations, what we see is that subject number 1 was randomly assigned to the HIIT group, and they have 2 data points, right? They have a pre-test observation and a post-test observation here in high-intensity interval training. They don't have any observations in aerobic training because they were not assigned to that group. So subjects are nested within group, while subjects are crossed with the factor of time. So in this sort of randomized controlled trial design, we would have one nested factor and one cross factor, or the other way to phrase that is that we would have one between subjects factor, which is which group you were in, and one within subjects factor, which is time. Was it your pre-test or your post-test? So we're going to talk about a number of different statistical designs in class in more detail, but working with this nomenclature of crossed versus nested is an important step in understanding how your data are structured. And depending on your research design, your research domain, you'll probably encounter a lot of the similar design, right? So if you're doing experimental work in a wet lab, you might have animals that are randomly assigned to different conditions, right? So animals would be nested within conditions, but then they're also measured over different time points. So animals are crossed with time, But then if you're doing more educational research, right, you might actually have students within classrooms and classrooms within schools, right? And then you now have time within each person. So you might have time within a person, but then people nested within classrooms, but you might also have people crossed within classrooms. If I have English students and calculus students, right? Some of those students take the same classes. So class might actually be crossed, but nested within schools. So it gets confusing, right? And you have to kind of work through the details of what kind of model you need to run. And you'll probably have kind of a toolkit of model designs that you employ in your own domain. But by working with this language of cross versus nested, it gets us to think about the structure of our data. And in the subsequent videos, we'll show you how controlling for this either crossing or nesting of factors, we can actually satisfy the independence assumption and correctly analyze our data.